feel good today, so I will give the lecture. What I'm going to do today is to go over what we've learned up to now, and I hope it's useful for your preparation of midterm. And because I will now talk about something new, so if you have confidence in yourself, feel free to leave, okay? I talked with a professor at the very beginning of the quarter. He said he will tell you guys about the exact date 2 weeks before the midterm. So he thinks it's good enough. So if you still have question about that, just send him email. First thing I want to talk about is the solution to the special Monty Hall problem. Hey. Obviously, over here you have a bunch of choices. You can open first door, you can open only one door, or only 2 doors, or all the 3 doors. So it's pretty clear that if you open only one door, the chance to get the largest amount of money is 1/3, is 1/3, right? Is that clear? And then the probability to get the largest amount of money by opening only 2 doors is the following. Let's say behind the second door. So this is an event. This event can be break down into the following. Because the largest amount is behind the second door, so it's not behind the first door, right? So this event can be described this way. Not behind the first door and behind the second door. So these are 2 events. So how to compute the probability of this event? We can do it this way. By using conditional probability, we can get this number like this behind the second door, conditioned on not behind the first door, times the probability of not behind the first door, right? Let's look at this probability first. So the largest amount is not behind the first door, so it should be behind either the second door or the third door. So the chance to get the largest amount of money by opening the second door is 1/2, right? Because you only have 2 choices left. So you pick one of them. So the chance is 1/2. So this probability is 1 over 2, and times not behind the first door. So at the very beginning, you have 3 doors to open, and you can open any one of them. And now the probability of open the door without the largest money is 2 out of 3, right? So the probability of this one is 2 over 3. And the final result is 1/3. Now let's look at the probability of the largest amount of money is behind the third door. Again, this event can be described as behind the third door, conditioned on not behind the first two. Times the probability of not behind the first two. Follow the same argument like over here, we can say this part equals the probability of not behind the second door, conditioned on not behind the first door. Times the probability of not behind the first door. Like we just said before, the probability of not behind the first door is 2 over 3, right? And the probability of not behind the second door, conditioned on not behind the first door, is what? 1 over 2. And now the largest money is not behind both the first door and the second door, and then it must behind the third door, right? So the probability of this guy is 1. So the final result is 1 times 1 over 2 times 2 over 3 is 1/3. Is this your final answer? Why?
It's not any better than the first door.
What?
It's not better than just choosing a random door.
We are choosing the random door. We are doing that. But, well, it's pretty obvious that there's nothing you can do, or there's nothing more you can do than opening only 1 door or 3 doors. Because in both situations, the result is fixed. But if you open 2 doors, you have choice. Let's say you open 2 doors, and the money behind the second door is less than the money behind the first door. And then what you do? If you stop, you're pretty sure to lose, right? But if you give it a third try, the largest amount of money might be behind the third door, right? Does that make sense? So if you stop, you lose. You try one more time, you may win. So over here, you can do something more to refine this strategy. Intuitively, you get a better chance to win the game. So let's say, what's the probability of this new strategy? Before we do the math, let me describe the strategy first. Basically, we first open 2 doors, and then depends on whether the money behind the first one, behind the second one, is larger than that behind the first one. You decide whether to continue. If larger, you stop. Why you stop? Because intuitively, because 2 out of 3, you've tried 2 out of 3, and now you get the larger amount of money behind the second door. So I have more confidence in the chance to win the game, right? And then, if less, you continue to open the third one. So this is the strategy. We can list all the possibilities, or in other words, all the ways to open the door to get, and say what's the chance to get the most money. This is door A, let's say less money, and B, and C, and this is our result. Let's say we open this one first, and then we open this one, and the amount behind door B is larger than this one, so we stop. Do we win or not? No. So we lose. And another way to open the doors is we first open door A, and then we go door C. And this one is larger than this one, we stop. Do we win or lose? We win. And then, because we randomly pick one door, so the first door can also be door B, right? Let's say we first open door B and then open door A. And the money behind door A is less than the money behind door B. So we continue to open the third one. And we stop over here. And we also win, right? Similarly, we go first door B and then door C. We stop over here, we win. And also we go, first we go door C, and then we go door B. And because this one is less than this one, we continue to go door A. And we stop over here, and we lose. And similarly, we go 1, 2, 3, we stop over here, we lose. all the 6 possibilities, there's equal possibility to open the doors with any of the choice. So the chance to win the game is 3 out of 6, right? So it's 1/2. It's larger than 1/3, right? So mathematically, how do we compute this probability? The probability of win with the strategy is win by opening 2 doors plus win by opening 3 doors. Why I can compute the probability this way? Because this event consists only these 2, and these 2 events are mutually exclusive, right? So the probability of this event is the sum of the probability of these 2. So let's look at this probability. Win by opening 2 doors. Can anyone give me some hint to compute this probability? Win by opening 2 doors. It's different from the probability we get a moment ago for opening only 2 doors. Over here, the difference is we may open 2 doors, but we also may open 3 doors. So this situation is one of the possibility to open 2 or 3 doors to win the game. So this event it seems it's hard to find out the probability of this event, but this event consists of 2 events. So what are they? Win by opening 2 doors and first open A, right? Plus win by opening 2 doors and first open B, right? Can I say, do we have another choice? We win by opening 2 doors, but we first open door 3. That's not correct, because if we first open door 3 and then we go a second door, and the money behind the second door is for sure to less than the money behind the first door. So this event consists of only these 2 events. So these 2 events, it's much easier to get the probability of these 2 events. Let's say win with 2 doors A is first. So what's the probability of this one? Because all the three doors can be opened with equal chance. So when with two doors, A is first times A is first, right? Because all three doors can be opened with equal chance, so this probability is 1/3, right? And then you first open door A, and then you open the second door to win. So that means out of the two doors left, you must open door C. But the chance to open door B and door C is the same. So this probability is 1/2, right? So the product of these two is 1/6. Similarly, you get the probability for this one is also 1/6. So the sum of the two is 1/3. Now this is the probability of this one. Let's look at the probability of this one. The probability of when with three doors. So this probability, again, you can break this event into smaller events, which can be when with three doors conditioned on first open when with three doors and you first open A and the probability of okay. A first, B second, and the probability of when with three doors, B first, A second, right? These are the only two possibilities to win with three doors. So you compute each one of them. So the chance you open door A first is 1/3, and then you go the chance to open the second door B as the second one is 1/2, and following the same argument, you get 1/3 times 1/2. So it's interesting. I check myself. It's Oh, no, no, no. Okay, I see where the problem is. So there's actually only one choice over here, because our strategy is if the money behind the second door is larger than the money behind the first door, we stop, right? So, so if we open A first and then open B, we will never open door 3, right? So this event is equivalent to only this one. You open B first and then you open A, right? So the probability is 1 over 3 times 1 over 2. So it's 1 over 6. And the sum of the two is 1 over 3 plus 1 over 2, 1 over 6 is 1 over 2. The same as what we get over here. With this example, the point I want to make is when you trying to compute some probability of event A, it might be difficult to get that number. So, but you may break this event into smaller pieces, because if you go a little deeper, you have more information. With more information, you can get the probability of smaller events. And if all these events are exclusive, and you add them together to get the number for this one. That's a point I want to make. So let's say events, smaller events BI, the sample space consists of smaller events BI, and then this probability equals and it can be computed as so compare these two, you have more information about this event, right? And maybe sometimes you need to go a step further from over here by doing conditional probability. Here you go, PA based on BI. The expression might be useful in some situations. Okay, now let's look at some class content. Would you please open your book to 181, page 181. Let's do some exercise together. And with these exercises, I want to emphasize some important expressions in your textbook. Okay, here is the problem. This is a function of random variable. Random variable y is a function of random variable x. So what you are asked to do is find
What number is it?
59 on page 181. Find the CDF, PDF of y in terms x, in terms of those of x. The second is what is PDF of y if x is Gaussian. Okay. So what's the definition of CDF? It's defined as the probability of random variable is less than or equal to this small y. So now you know what is this random variable in terms of the other random variable. So you just plug this in this formula, and you get Ex less than y, right? So you know the distribution of x. So to compute this probability, you must try to transform this expression in terms of the distribution of variable x. Let's plot this function. Let's see, this is x, this is y. This is the curve for the function. So when this function is less than y, let's say x. Let's say y is over here. You draw a line, and then this is a projection of this point. Obviously, if random variable x is less than this guy, let's call it small x, and then Ex is less than y, right? So the probability of this one is the probability of, let's call it x, okay? So gives less than x, right? So what is this x? You know, y is over here, this point, because this point is on this curve, so it must satisfy this condition, y equals e to x, and then small x is to ln y, right? You plus this back in, you get less than ln y. And, oh, sorry, that's all you could do. And this is a definition of CDF in terms of capital X, random variable x, so it's ln y. This is a pretty standard derivations for the distribution of a function of random variable. So you follow the same step. You follow the same steps. You first you use a definition of CDF, and then you plug in the function, the definition of the function, and then from over here you find out what is the equivalent event in terms of this random variable, and you get your final result. because this function is monotonically increasing. So this one less than y is equivalent to x is less than, well, let's put it in a general form. Let's say y is some function of x, okay? Now what you do is the probability of less than or equal to small y, you plug in the definition of the function. If this function is monotonically increasing, you can get the probability in terms of random variable x right away in this form. The inverse function of g, right? This is the inverse function of g. So you use the CDF of you use the definition of CDF. You get a CDF of random variable y in terms of that of random variable x. Well, our assumption over here is this guy is monotonically increasing. And then what is the CDF? The CDF is the derivative of this guy with respect to y, and you go d f x y dy, right? And use chain rule. G minus y d g times d dy. So in many situations, you can use this formula to get the CDF and PDF of random variable y. So what if this function is monotonically decreasing? So if it's monotonically decreasing, so which part should be changed? This part, from here, this step, from here to here, right? So what you do is y equals p g x y, and you go, because it's monotonically decreasing, so x should be no less than g minus 1. This guy is 1 minus x g, right? And what is this? This is keep to x g minus 1. Let's see, minus. Why did I put minus over here? Because this is just less, not less than, not less or equal to. Because if it's a discrete random variable, there might be some probability lies in that lies on this value. So I just put minus over there because to stand for this situation. And if you want CDF, you just use this definition. You get the CDF for this one. Well, for general situation, you have to find out what's the equivalence of this event. Let's say f y gx less than or equal to y, and you have to find out the equivalent event of this guy. Let's say gx is x squared. So the standard way to do that is to you first plug out the curve of this function. Oops. This is x. Let's just say random variable gx. And then suppose if y is less than 0, and then the probability is 0, right? And if y is larger than 0, it's, let's say y is over here, and then the probability of gx is less than y. You draw a line over here, obviously when x lies in this interval, gx is less than y, right? So you compute the probability of random variable x lies in this part. So to do that, you have to figure out what is the value of this point and this point. Well, it's pretty easy. It's minus square root of y and square root of y. So in this situation, let's say it's over here, the probability of this guy equals probability of less than or equal to square root of y minus square root of y. And this with a PDF or CDF, you can compute this y. Let's just express it in terms of CDF. This guy is equals to keep to x minus less, right? Is this clear from here to here? This is minus, less than minus. So with the definition of CDF, this is fx. Right. Let's look at a more involved situation. What if the function is defined this way? X minus plus 1, x minus 2, x minus 5. So again, first you plot out the curve of this function. So this function will cross x axis at 3 points. One is -1, is 2, 5. So it's going to be something like this. Let's say this is something like this. And now give a number, give some less than or equal to y. And then, just like before, suppose this is y. You draw a line. And when will this event happen? It happens when random variable x lies in this interval. Let's call it I1. Oh, I'm sorry. This interval from infinity up to this point, let's call it I1, and this interval, I2. So this probability equals to the probability of x in I1 or x in I2, right? Because these two events are mutually exclusive. So probability in I1 plus probability of x in I2. And with this function, given this value, you can find this value and the coordinates of this one and this one. And then you get the definition for these two intervals. And then you use the definition of PDF or CDF to get the probability. So with this example, we just studied how to compute the CDF or PDF of the function of a random variable. If the function is monotonically increasing or decreasing, it's pretty easy. You just, without going through the details, you just plug in the this expression over here and over here. And so what if the form of that function is more general, let's say x to the power of 2 or something like this? The way to do that is you plot out the curve of that function, and by doing that, you find out the equivalent event of this one. And then you use the definition of CDF or PDF for random variable x to get the CDF or PDF of random variable y. Okay. Next, let's look at problem 17.4. This is a very easy problem, and with this exercise, I want to emphasize some very useful formulas. let's say random variable y is defined as cosine omega t plus some constant c, and omega c are both constant. A is a random variable, and the mean is m, and the variance is sigma square. So the problem is to find the mean and variance of capital Y. So E capital Y cosine omega t plus c which equals cosine omega t plus E, right? So how can I get this equation from over here? So we use the formula the sum of two random, the expectation or the mean of the sum of two random variable is the sum of the mean of the two random variables, no matter they are independent or not. It doesn't matter. That's how we arrive here from this one. And then from here, because this one is constant, right? So basically we get E A times omega t. This one is constant, so it's just plus c. And how can we get this result from over here? We use this one. Let's see. Suppose alpha is some coefficient. We have this conclusion. That's how we get this result from over here. And then, because the mean of this random variable is m, so we plug in omega t plus c. Okay, this is the mean of random variable y. So what is variance of y? Well, obviously, you can use a definition of variance. Y square. But you can do it the other way, which is minus sometimes this formula might be more useful because, I mean, in your exam, I mean, the professor usually, when he asks you to do the variance, I bet he will also ask you to do the mean. Because first, you've already got the mean, so you just do this part, right?
Quick question. I'm sorry, why were you able to pull the cosine omega t out of the expectation?
Because this part is constant.
Oh, it is constant. Okay.
Yeah.
Constant.
Yeah. This that's our assumption. Omega, c are both constant. And then we use this formula.
But t is not constant.
Well, let's say t is it's like it's like some noise, and from time to time, the distribution of the noise is, the noise from time to time is a random variable, okay? But at that time constant, it's some fixed random variable, and the distribution depends on that t.
So we're looking at some time t. What is the expectation?
Well, let's just draw a figure of this. This is some omega c plus c, omega t plus c. Here is some constant, and let's say this is omega t plus c, right? This is m times omega c plus t, right? This is the mean. As time goes, at any time instant, this part, the mean of this random variable is y. So it can go like this,
Oh, I see.
you know.
Okay.
So at this time, it can be, at first sample pass, it can assume this value. If you do the experiment a second time, under the same condition, it can go, this mean it can go like this. So again, at this time instant, it assumes another value. The mean of the value is this guy. This is a concept of some random processes. You will run into it later. Now we are looking for the variance of random variable y. So the variance of y equals y squared minus square. So it's just because we've already got this one, so we just find out this one. You plug in the definition of y. You go a to the power of 2 cosine okay, and what is this? This is cosine omega I'm sorry. And this part is m, and you just leave this part, and you plug in this part. You plug this part back in this part, and what we can get. minus the square of this guy. So let's say what you get. You get minus so this equals so what is this? This is the variance of A, which is sigma square. So it's sigma square cosine omega t 2 square. This is the final result. And so in addition to these two formulas, this one is also very useful. Suppose the mean of a random variable is 0, and then it doesn't need to be 0. Let's say the variance of this guy equals alpha square variance A. This is another formula we did not use over here, but it's also very useful. You can apply these three right away if you need them. Now let's look at problem 83, page 182. Okay, let's have a 10 minutes break. 182. This problem is about Chebyshev inequalities. The problem is, suppose the lifetime of light bulbs have exponential distribution. So, and the mean of the exponential distribution is Ex. Let's call it lambda. So, because exponential distribution has only one parameter, which is the mean of the random variable. So with this information, we can write down the distribution of that exponential random variable, which is lambda e to lambda x. Okay. Now, there are n light bulbs, and we do arithmetic average of y, and y is sum of the lifetime of all the lights. So y equals xi from 1 to n, right? So what is the expectation of random variable y? We use this formula, right? We use this formula. Right? Because all the lights, all the lifetimes of all the lights have the same distribution. So the mean is the same, which is lambda. So what we have over here is lambda, which is lambda equals Ex. Now let's find out the probability of this event. Larger than A. So this probability equals right? Because we just find out the expectation value of y equals the expectation or the mean of random variable x. So you get this one. And with Chebyshev inequality, this probability is less than or equal to the variance of y over a square, right? So we need to find out the variance of this random variable. So it is right, and use this formula over here, we get n squared 1 over n squared xi. Okay. This is how we get this result from over here. And now, what we know is all these n random variables are independent. In that situation, we have another formula. Which is if xi are independent, then variance of the sum of them equals to the sum of the variance of each individual random variables. So we use this result. 1 over n squared So what's the variance of exponentially distributed random variable? It's this part is 1 over lambda squared. So we get n squared lambda square. So it is n lambda square, right? So we plug this back in this formula. We have over 1. So the next question is what happens as n goes to infinity? So what happens? What's the value of that probability when n goes to infinity? So oh, I'm sorry. Here is less than or equal to. Okay. This is inequality. So when n goes to infinity, this one goes to 0, right? Go to 0 as n goes to infinity. So what does that mean? That means given some small number, okay, this is the probability of the random variable, let's say uy, this is y, because this one is a random variable, okay? Let's say this is minus a, this is a. No, this is ey plus a is ey minus a. These 2 points. This probability is the probability of this random variable lies outside this interval, right? The probability of the random variable lies outside this interval. But you can say as n goes to infinity, for any small number of a, that probability is 0. So that means you can give this a sufficiently small, okay? So in that situation, y will converge to the mean of the distribution, right? That explains why you can estimate the mean of the lights this way. Does that make sense? Okay. Suppose this is some A1. Now we go another value of A. We go a smaller one, right? This is E1 minus plus A. This is EY minus A. No matter how small A is, as long as it's not 0, we can choose some large enough number of experiments to give a good estimate of the mean, because the probability of that value lies outside this interval is 0, goes to 0. So it must lie within this within this interval, and this interval is the vicinity of the mean, right? So that's why we can use this method to estimate the mean of the random variable. So this is just some application of probability theory in real world. Mm-hmm.
On the bottom right hand of the board, should that be n squared minus squared?
This one?
Yeah.
Because all these random variables have the same distribution, so they have the same variance. This is the variance of any one of them. There are n of them. Okay, so this is actually now let's go to chapter 4. And over here, I just emphasize some a basic definition of joint CDF of several random variables. Let's take the example of 2 random variables. But the definition can be easily generalized to several or more than 2 random variables. CDF is defined for homework number 2. For homework 2, you basically play with the definitions. So as long as you are familiar with all these definitions, I think you won't have any problem. It's more like a math class instead of probability class. It's a marginal CDF. They defined as this step is very important from here to here. This tells you from joint CDF, how can you get the marginal CDF, right? You just trying to find out the limit of this function and y goes to infinity. That's the y. That's the way you get marginal PDF. Okay. Similarly, you can define the marginal CDF for random variable y. When all these random variables are continuous, we can define the joint PDF of these two random variables. The definition is this. And the marginal PDF is defined as F as a derivative of marginal CDF with respect to x. So you go d dx this part and which equals to this one. All you need to remember is marginal PDF equals this. This is how you compute marginal PDF from joint PDF. Just from this is the way you get this result. But what you need to remember is here. Next, we talk about independence. Random variable x, y are independent if and only if. That means this is a sufficient and necessary condition. X, Y, X, Y. The joint CDF is a product of marginal CDF. In homework number 2, you are asked to prove two random variables are independent. This is how you can prove the result. So basically, you find out the joint distribution, and you find out the distribution, the marginal distribution, and then you improve they equal to each other. If the two random variables are continuous, then the definition is given in terms of PDF. All these definitions can be generalized to more than three random variables. Now let's look at exercise 9 of chapter 4. Okay, here's the problem. X, Y are two random variables, and the joint PDF is AX per B, Y, B, Y squared. Okay. X, Y larger than 0, A, B larger than 0. The first question is to find CDF. Joint CDF. The second question is to find the probability of random variable x is larger than y. And the third one is find the marginal PDF. This is a problem of basic definitions. So let's go over the definitions. So the joint CDF is defined as probability of the integral of 0 to x, 0 to y, A, why did I put 0 instead of minus infinity? Why is that? Yeah. You must be careful about this part. So, well, you can use minus infinity, and then because the integral equals 0 plus 0 to x, and this part is 0, so it's the same. Okay, what you can do from here is AU du times right, and this is this equals to so the final result is 1 minus e to the power of minus a x squared times 1 minus e to the power of b y squared. For the second question, we are asked to compute the probability of x is larger than y. Let's say this is a play of all the possible values of these two random variables. And in what part will this event occur? Let's draw a line. This is y equals x. So obviously, if the random variable pairs lies in this area, this event happens, right? So we compute the probability of the point lies in this area. So this goes back to calculus. It's from 0 to infinity, and then x. And you do the math. This is this one. And when you do marginal PDF, first, I just erase it. First you do marginal CDF. Marginal CDF is that y goes to infinity, and from the joint CDF you get marginal CDF, and by looking for the derivative of marginal CDF you get marginal PDF. So this one is what we have over here. So it's limit as y goes to infinity okay, as y goes to infinity, this one goes to 0, right? So equals, right? And then the marginal PDF is defined as the derivative of this guy with respect to x. Limits y goes to infinity f(x, y, x, y). So it's a derivative of this function. And it's this. Similarly, you can find the marginal PDF of random variable y. One last point I want to make over here is how to understand PDF. So like we've learned in class, PDF is defined for a continuous random variable. Let's say, take the example of uniformly distributed random variable. Let's say it's uniformly distributed over 0 to 1. So the random variable can assume any value within this interval. But the probability of that random variable assume any specific value, that probability is 0. Why is that? Because the probability of that random variable lies in this interval is 1. But there are infinity number of points within this interval. They share this probability evenly. So 1 over infinity, what do you get? You get 0, right? So PDF doesn't tell you the probability of this random variable assume some specific value. It's just a tool to compute the probability of that random variable lies in some interval within this range. Okay, let's say this is 0.5, 0.7. The probability of that random variable assume any specific value within this range is 0, but it lies in the probability of that random variable lies in this interval is not 0, because there's also infinity number of points within this range. So in this situation, it's infinity number of zeros. It goes to some specific value, not 0. So with the definition of PDF, how can we compute the probability of a random variable lies within this interval? It goes this is how you use PDF to compute some probability. Any questions? Which part? I think he's right. This one?
Yeah. Divided by 3x.
Okay, let's see. Oh, I see. Thanks. Right?
The third one, the third. The final result.
Right. If you don't have questions, that's all for today.